Exercise 17. So here we have to prove that if our n is at least 5, then the alternating group of degree n is the only non-trivial subgroup of Sn. So let's see the solution. That means in all the symmetric groups Sn, where n is at least 5, the only normal subgroups are An, Sn and the trivial group. So we start off the solution like this. Choose distinct symbols A, B and C from the set of symbols on which we are actually considering permutations in Sn. Now, having chosen 3 such distinct symbols, also choose further distinct symbols D and E, again from the set of n available symbols, but now D and E are different from the previous choices. And note that we can do this because n is at least 5. So even when n is 5, we will be able to make these 5 choices. You can see that the way we have chosen these things, these symbols, we need 5 distinct objects. So that we have. At least 5 of them are there. Okay. Now, we claim that the three cycle A, B, C is equal to this product. Oh, okay, we may confuse E with the identity element, so let's just consider this last symbol as F. Okay, let us now see if this is actually the case. Note that this transposition D, F, it has appeared twice. So that means this will just simply give us the identity element. That means this beetle 2 transpositions will actually vanish, but there is a purpose for writing them here. So while calculating this product, we need not even consider this middle 2. We can just simply calculate B, C times A, B. Now let's see if we are really getting this 3 cycle. The first transposition does not change A, and then the second one changes A to B. So A goes to B. Then the first one changes B to C, and the second one then further does not change C. So B goes to C. And finally, the first one changes C to B, and then the second one changes that B to A. So C goes back to A. So yes, it's okay. Since the 3 cycles in Sn generate An, and this is coming from a previous exercise. I think it is, what is that exercise number 12, by exercise 12, it follows that An is equal to the subgroup generated by these products, where in SN of course we have to mention that such that alpha, beta, gamma, delta are distinct. The subgroup generated by this type of products is AN. But exactly how? Let us see. What is this equation telling us? This equation is telling us that any 3 cycle is a product of 2 elements of this type, where alpha, beta, gamma, delta, these are all distinct. Do we have distinct things here? You see, B, C, D, F are all distinct, 4 distinct elements, and then D, F, A and B are also distinct. So that means that this 3 cycle, which is actually any 3 cycle, belongs to this subgroup. Why? Because it is a product of 2 elements of this type, and this is in fact the subgroup generated by the set of such elements. So that means all 3 cycles belong to this subgroup, but the 3 cycles generate AN, so AN will be contained in the subgroup that you see on the right side of this equation. Conversely, you look at this subgroup, and in fact you look at the generating elements. The generating elements are what? They are products of disjoint transpositions, that is disjoint 2 cycles. Product of 2 cycles, all of them are even permutations. That means any such elements, the generating elements, they are all even permutations. So they are in fact all in AN. By the definition of AN consists of all the even permutations. So the subgroup generated by them will also be contained in AN. And just now we have said that AN is also contained in this subgroup, that's why they are equal. Okay, so we let it sit like this. And now we do something else. We will be needing this. Now our aim is to show that in this type of AN, where n is at least 5, the only non-trivial normal subgroup is AN. Now we move towards that goal. So for that, now what we do, now we consider a normal subgroup N which is non-trivial in Sn. So our aim should be to show that N is either AN or Sn. Then the claim will be proved. Now because N is non-trivial, there will be a non-identity permutation, some element in N which is different from the identity element. So we choose one such element, sigma, not equal to the identity permutation in N. Because sigma is not the identity permutation, so there exists some I among the available symbols such that I is mapped by sigma not onto I. That means sigma needs to change something in order to not be the identity permutation. It needs to change something. So let that such something be I. Okay. Now choose a symbol J that is different from both I and I sigma, both I and the image of I under sigma, and such a choice can of course be made. N is at least 5 and I mean, if you just remove 2 from them, you can obviously make another choice. Okay. And we are going to define tau to be this 2 cycle I comma j. Okay. Now we look at the product sigma inverse tau sigma tau inverse. Then let me keep this one at least because we will need it. Then sigma inverse tau sigma tau inverse, which can be thought of as sigma inverse tau sigma, and along with that tau inverse, and this becomes equal to sigma inverse tau sigma becomes I sigma comma j sigma, and tau inverse, because tau is a transposition, its inverse is itself I comma j. How exactly we are getting this, I am coming to that. But before that, let me just finish this sentence. Note that sigma inverse tau sigma tau inverse belongs to N since N is normal. Okay, now there are two things to note here. The first one is this calculation, of course, and the second thing is that this product actually belongs to N. So let us see this one first. Why does this element belong to N? And also we are justifying it by saying that N is normal. Let's see why. Okay, so we have chosen sigma from where? N. So you can in fact think of this product as the product of sigma inverse and tau sigma tau inverse. Because N is normal, so tau sigma tau inverse will belong to N, because that's just what normality is. And sigma already is in N, so you take the product of this element of N and the inverse of this element which is also in N, so this belongs to N. Now we come to this part. We understand why tau inverse is this, I comma j, same thing, tau inverse is the same as tau. But what about this? Originally tau is what? This. Now if you apply sigma inverse tau sigma, I mean if you do this to tau, then it becomes this. This is actually a fact which either you can directly see, or in order to understand this, you go to the last part of the next section where we have been mentioning it and we have actually mentioned it quite a few times, that there is an equivalence relation in any group called conjugacy. And if one considers that equivalence relation in the class of symmetric groups Sn, then one gets the result that in Sn precisely those permutations are conjugates of one another that have the same cycle structure, and in that discussion you have this thing. Okay, So if you take a permutation tau, it's not, this is not something that happens only with 2 cycles, but for any permutation. If you consider a permutation tau like this, and you take its conjugate, because sigma inverse tau sigma is a conjugate of tau by the definition of conjugacy, then it becomes just this, where what you do is that you replace the symbols with their sigma images. It happens, this is a fact. So that's what we have used here. Okay, and this particular product, it looks like this and it belongs to N. Now what? Let's see. So that means we have got a particular type of element in N, whose cycle structure is this, although still we cannot say that it's a cycle structure, because we don't really know whether these are disjoint cycles. Now that fact will come. But before we guess whether this is disjoint or not, something else, okay, yes. Since I sigma is not equal to J sigma, why? As I is not equal to J. Why is I not equal to J? Because you see, according to the choice of J, J is different from both I and I sigma. So J is not equal to I, and sigma is injective. So that is why inputs are different, so outputs must also be different. Since this is the thing, and I sigma does not belong to the set consisting of I and J. Because of these things, I sigma does not belong to this. That's because I sigma cannot be equal to J, because that's how we have chosen J, and I sigma is different from I here because of this. The product, or we can just simply write the element, this element is a product of two distinct 2 cycles. Okay, so it's a product of 2 distinct 2 cycles. Now if we do not have this distinctness, that means if these 2 cycles are actually the same thing, then this is nothing but the identity permutation. That's because the square of any 2 cycle is identity. So that means whatever element we see here, we are seeing here, that is a non-identity element in N, and it's a product of 2 distinct 2 cycles. Disjoint or not, that we are not saying now, but distinct 2 cycles. Now if it happens that just like I sigma, J sigma also does not belong to this set consisting of I and J, then it becomes a product of 2 disjoint 2 cycles. Is a product of two disjoint two cycles. Okay, now what happens? Now you again think of the relation of conjugacy. Let us recall, because we are going to use it here, that for any two elements A and B in a group, they are called conjugates of each other or conjugates to each other if B is equal to C inverse AC for some element C in the group. And it turns out that this relation is an equivalence relation. So if B is a conjugate to A, then A is also conjugate to B, because the relation is symmetric. And in fact you can see why that is so. You just take C inverse to this side, so you get A equal to C inverse inverse C inverse. So by definition, A becomes the conjugate to B. Now what do we have? Let us see. The thing that we have so far not got, which and in fact we are going to see in the next section, that is conjugacy in these symmetric groups. According to that thing, in a symmetric group, the elements having the same cycle structure are conjugate. In particular, all the elements that look like this, which are products of two disjoint two cycles, are conjugate. That means they form a conjugacy class. Another conjugacy class would be, for example, the class formed by all three cycles. Then maybe there is another such class where we have those types of permutations, each of which is a product of two disjoint cycles. One of them is a 3 cycle and the other one is a 2 cycle disjoint. Okay. Now what do we have here? What is our final situation? The situation now is this, that we have obtained an element in N which now is a product of two disjoint two cycles. That is one thing. So that means now we know that the cycle structure of our elements is this 2, 2. That means it's a product of two disjoint two cycles. Okay. So all the elements in Sn which are conjugate to this one will also be products of two disjoint two cycles according to this theory that we are going to see in the next section. But how do those elements look? They naturally look like this. If we are calling this element something, this is the element, but just for the sake of writing things quickly, if we call this product say P, then any conjugate to P looks like this. Say let me take C itself, where C is coming from Sn. In other words, all the permutations which are products of two disjoint two cycles, each one of them, they look like this. And in this, when you look at all such elements which have this structure where C is varying over Sn freely, you actually are getting all those permutations where each one of them looks like this, a product of two disjoint two cycles. Okay, but where is our P? Our P is in N. So C inverse PC, all of these elements will also naturally be in N, since N is normal. That means all products of two disjoint two cycles belong to N. Okay, but the subgroup generated by precisely such elements where each one is a product of two disjoint two cycles is An. So that means because all such generating elements have now come inside N, so this An itself will be contained in N. So that's what now we are going to write. in the next line like this. Since any two products of two disjoint two cycles are conjugates and n is normal, so n contains all such products. Any two products of two cycles in Sn that we understand are conjugates and n is normal. N contains all such products. So by the first paragraph, in fact, this is where a paragraph ends, and then we started with n in another paragraph. So by the first paragraph, An, which is the subgroup generated by such elements, now that all the generators belong to n, this becomes a subgroup of n. Okay, but keep in mind all this conclusion comes from this condition. If J sigma is neither I nor J, then we have this. But what happens if this is in fact either I or J? If J sigma belongs to this set, then the product So the use of this fact is only in showing that this is contained in n in that case. Now we are going to argue differently. Then the product I sigma j sigma I comma j is a 3 cycle, which you can verify. Okay, you just have to take either I here or j here, and then you calculate the product. You will see that you are getting a 3 cycle, much like how we got a comma b comma c in that form there. So now, although the argument, I am saying that the argument is different, but it's similar to what we did here. There we had products of two disjoint 2 cycles. Here we have 3 cycles. Just the cycle structure is different. Strategy is same. Since the 3 cycles in Sn are conjugates and n is normal, all the 3 cycles are in n because one of the 3 cycles, which is this thing, now it is a 3 cycle, it's there in n. So normality of n and the fact that all the 3 cycles are conjugates to one another imply that all the 3 cycles are now in n. But just like these elements we have proved generate an, we already know from a previous exercise that all the 3 cycles also generate an. So without even mentioning that, we just simply directly write hence an is contained in n. Ideally, we should mention the fact that the 3 cycles generate the alternating group, so that's why this thing is happening. But that is understood, that's known. Okay, so now we have got unconditionally with the, whether this J sigma is one of them or is not any of them, without any condition, we have this fact. Okay, an is contained in n. So the order of an by Lagrange's theorem has to divide the order of n, and also the order of n of course also has to divide the order of Sn, which is n factorial. And because of these two divisibility relations, there are only two choices. Either n has to have order equal to this or equal to this, and accordingly n either should be equal to an or it should be equal to Sn. So that completes the solution. Hence or n is equal to Sn. So this completes the solution. Let us now also see the next one, but before that I need ink. Okay, now next we are going to see something called permutation representation of a group. So there is a paragraph where Herstein writes Cayley's theorem. That means theorem 291 asserts that every group is isomorphic to a subgroup of A of S for some S. That means, yeah, that's what Cayley's theorem is. It tells us that we can always choose, there exists a set S for any given group such that we can find an isomorphic copy of the group inside this permutation group A of S, consisting of all one-to-one onto mappings on S, where the binary operation is composition of mappings. In particular, every finite group can be found inside some SN. Every finite group can be realized, okay. As a group of permutations. That means can be realized as a subgroup of Sn for some n. And this realization of the group as a group of permutations as given in the proof of theorem 291 is called the permutation representation of G. This realization, let me just give me a moment. This realization of the group as a group of permutations as given in the proof of theorem 291 is called the permutation. I don't really know why the ink is acting up like this. Where is it all going? Is called the permutation representation of G. Okay, so first of all, let us try to understand what is being said here. This part, of course, we understand, and we also know that in the proof of Cayley's theorem, where we start with a group G, actually the underlying set of the group, that is G itself, is taken here in place of S. But do you recall what we did in the proof of Cayley's theorem? We did something like this. No? To each element of the group, we associated one function. That is, this was our group G. Now, for any G in G, we defined a function tau G from G to G like this. X tau G is defined to be equal to xg, where of course this x is coming from G. So that's how we set up a correspondence between the elements of G and the elements of A of G, that is the group of all one-to-one onto mappings from G to itself, and it turns out that our tau G defined like this actually belongs to A of G, and then this mapping psi which maps G into A of G given by this thing, it turns out that this psi itself is a homomorphism of G into A of G, which actually is an isomorphism, that means a one-to-one homomorphism. In other algebra texts, isomorphism means one-to-one as well as onto. Here, however, isomorphism means only one-to-oneness, injectivity. So the thing is that G finds an isomorphic copy inside A of G, and under this isomorphism, the element G in G corresponds to the function tau G, which is an element of A of G. So whatever the elements of G are doing inside G, their corresponding images tau G, say you take another element tau H in G, correspondingly you have tau H, they also do something similar in this other universe. So instead of seeing what goes on in G with some elements there, you can look at what their images are doing in this other universe. So they are being represented, these elements G are being represented by permutations, because these are permutations of G, and this association is a permutation representation of G. That is, we are representing G inside this other group as a subgroup. Technically speaking, this psi itself is called a representation. Now we will be asked in the coming few exercises to find permutation representations. So let's see the next one, where we are being asked to calculate the permutation representation of a finite cyclic group. Exercise 18. Find the permutation representation of a cyclic group of order n. So we need to find this. That means we just need to calculate tau G for every element G in our cyclic group. Calculating that is equivalent to calculating this psi. So we will then have our permutation representation. Let G be a cyclic group of order n, B a cyclic group of order n. That means A is a generator whose own order in G is n. Now let capital G be this element E A square Let's take some time to understand this. what does it even mean? You can clearly see that we have written a cycle here. What is A of G? A of G is the group of all permutations of G. That means the elements in the group G themselves are now being taken as symbols, and we are considering all the permutations of those symbols, and those symbols are nothing but these. These are because these are all the elements of G. So whatever you are seeing here is actually a permutation of those symbols. That means, and it is this cycle. Okay, it could have been something else, but we need this cycle right now. So, and we are calling that cycle G. So it is an element in A of G. Then with this element, it turns out one can calculate that the first thing is of course very easy. Tau of the identity element is identity element. You need to understand that this identity according to this setup is this identity element in G. That means A to the power 0. And this identity element is the identity permutation in A of G. Then tau G is actually G itself. Okay, and oh sorry, what the hell have I written? Tau of A is G, because here we need the elements of G. Tau of A turns out to be equal to G. Tau of A square turns out to be equal to G square. See how nicely it is coming. And it goes like that. And tau of A to the power n minus 1 turns out to be equal to this. With this, the permutation representation of G is just that map. A of G, note that because G has how many elements? N elements. So A of G actually is isomorphic to the symmetric group of degree n, and our psi of course is this map. Tau A to the power I. You can understand why the images turn out to be like this, powers of G, because we are trying to represent G inside a permutation group. Our original G is cyclic, so whatever image it has inside A of G, that should also be cyclic, because they should be isomorphic to each other. And that cyclic group inside A of G, it turns out that it has the generator G, which is this n cycle. Okay, so with this is the permutation representation, and here we end the video. But before I end things, actually I want to say something about this representation. Whenever we have some abstract group where we say have such symbols, formal symbols, there is a binary operation for combining two such symbols to give us a third such symbol, and the group axioms are verified, so it becomes a group. It's usually better to try to understand the abstract group by finding it somewhere else which is more familiar to us. Say, it's really, I mean, in this simple case, it is simple that you look at a cyclic group of order n where the elements have this simple structure. All the elements are integral powers of a single element, but in some quite complicated abstract group where we are playing with symbols, things can quickly get very confusing. It's usually better to represent the group or look at its isomorphic copy or analog of the group somewhere else which is more familiar to us. Instead of looking at abstract symbols, it's much easier to understand permutations with which we are more familiar. So we represent the group somewhere else. So this type of homomorphisms give us representations, and in general they are called representations. Here we are representing the group inside a permutation group, so that is why a permutation representation we are getting. Like that, other representations are also there. And in fact, here itself in this exercise that we are next going to see second permutation representation, then coset representation, where the right hand side group will be different. There is another type of representation which in general is called representation or linear representation, where on one side you have your group, whatever it is. On the other side you have a group of matrices, say something like this. A general linear group of n by n matrices, non-singular matrices with real entries under matrix multiplication, and the representation is a homomorphism. But once you have one such representation, so then what you do, here you are instead of looking at group elements, you are looking at permutations. Here, instead of looking at group elements, they will be looking at an n by n matrix. What is the benefit of considering matrices? The benefit is that you can turn a group theory problem into a problem in linear algebra, which is very well understood. If one goes one step further and takes the trace of this matrix, then one gets a function from the group into the field R. This type of functions are called characters. Characters of the group. Many results in group theory which are quite deep essentially depend on properties of characters. If your underlying field is in this setup, if your underlying field is a field of characteristic 0 like R or C, the field of complex numbers, then you get such representations. But if your underlying field is a field of finite characteristic, then also you get some representations which are modular representations, okay, which have some well developed theory. This is a very big subject, and one needs to consider representations and characters if one wants to learn the deeper parts of group theory. One more thing is there. When you hear things like this, group theory has applications in physics, in chemistry, crystallography. What the people from those fields do, they mainly rely on representations. Exactly how, I also don't know, but representations are very important, particularly to particle physicists, because of some reason. So I just wanted to say these few extra things. So in the next video we are going to of course solve the other. And now some problems that will come after this, all of them will ask us to find these permutation representations. So with that, I just end the video. Tomorrow is Saturday, so let's do Gallian's ring theory problems tomorrow, and then day after tomorrow we are going to do analysis. So that's just all. I wrap things up for tonight with this. So see you tomorrow with Gallian's ring theory exercises. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.